List cost substitution is by far the easiest rule in Solid to explain. And it's generally defined that two implementations of the same protocol or with the same API can be swapped without unexpected behavior changes. So what this is saying is if a class is using a protocol and you change from one implementation of that protocol to another, your class shouldn't really be affected. The point of a protocol is to shield other pieces of code from implementation detail. An incorrectly implemented protocol would prevent that shielding. You can think of protocols like contracts. They make two things agree to a common set of rules about how those things will collaborate. Much like in law, if you have a contract, but one of the sides of the contract does something unexpected, there's going to be trouble. But at least your code is probably less likely to have to go to jail than someone in a law contract. A good example of list cost substitution is around circles and ellipses. So an ellipse can vary its width and its height independently. It would have an API quite like this. A circle is a special case for an ellipse, so it would make sense to make a class of circle which extends the ellipse class. However, circle as a class and as a concept will break the contract of an ellipse. This is because a circle cannot change its width and its height independently, so you're either going to break the definition of a circle, that the width and the height are the same, or the implicit assumption that setting a height will not affect the width. Thus, a subclass of an ellipse cannot be substituted for ellipse without an unexpected change in behavior for someone trying to use that class. The most important point here is that the modeling is wrong, as an ellipse has two axes that can change, its width and its height, but circle actually only has one, which is its radius. So in this case, it doesn't make sense that we're treating a circle as a subclass of an ellipse, no matter how convenient that may look. This is a contrived example, but there are others. For example, a method which takes a callback and the assumption of which thread that callback is called on. If the code assumes that the callback is called on the main thread and thus does some UI updates in that callback, another implementation that calls the callback on a background thread will firstly break that assumption and secondly break your UI. So here's an example of a protocol where two implementations would violate list cost substitution. We have a loader which loads a list of animals and the result comes back via this callback. Note that right now the result is of type any or error, and this is one of the problems that we have in this list cost substitution example. So we can either load animals from user defaults, which in this case returns us a string array, or there's one that loads animals from the network, say from an API. That one returns a map. So immediately we make an assumption about what this load animals callback gets called with. The user of this protocol has to handle both cases. So instead we should probably tighten up that protocol and we'll make it return a specific type. And we'll have to change the implementation of the network loader in order to do that correctly. We'll just assume that the API has changed and it returns us a list instead of a map. There's a second assumption here, which is again implicit, that any errors will come back via the callback. This assumption is correct in the case of the user defaults. If there's no animals, then it throws a no animals error. However, for the network loader, if there's a random error or there's no data, then actually we have a precondition failure rather than passing the error through the callback, which is what we assume. So instead of a user of this API getting a surprise crash when they use the network loader, we should route the error through the callback instead to avoid any surprises. Another easy principle to understand, but interesting to implement in real life, is interface segregation, which is the fourth part of Solid. This principle talks about how, instead of having large protocols, you should split them down into smaller, more singly responsible ones. Which is basically saying one tool shouldn't do everything, and each of your tools should have a specific purpose. If you've ever used Objective-C, you'll remember that NSObject has methods for equality and hashing building. If you wanted to implement equality, by convention you implemented the hashability as well. In Swift, however, things like this are split out into multiple protocols, such as equatable and hashable, so that if you don't need one, you just simply don't have to implement it. The codable protocol is another great example. It's segregated into two smaller protocols, encodable and decodable. If you only need one of them, then you only have to implement one of them, but the codable protocol is there in case you need both. That way, you don't have to implement functionality you're not interested in. As the saying goes, only the code you don't write can't have bugs in it. You'll notice all the protocols we've discussed end in able, such as codable, hashable. This is a really useful way of working out roles and responsibilities using protocols, and the term is actually called role interfaces. If you ever want to try and split up an interface, such as what we'll see here today, then thinking of each of these able interfaces that you can split it out into will make it a lot easier for you to split it out. Let's take a look at UI Table View Delegate, because it's a really big protocol. Each year there's another couple of methods in it, and it could really do with some segregating. Because it's this long. Luckily, because this protocol is an Objective-C one, we don't have to implement every method in it. However, if we did have to, then that would take a lot of unimplemented methods and a lot of code. So visiting the API documentation for UI Table View Delegate gives us some really big hints about how to split this protocol out, because it's split into separate sections. For example, with these ones around editing, this could be called the cell editable protocol. Or for example, with these ones around the context menu, these could be called the UI Table View Context Menu Delegate. You can't always make an able interface from it, but you can try. It's good to point out that if these were split into smaller and tighter protocols, then actually using the protocols would not be much different. You just have to set each one individually. And also the table view code would be easier because it wouldn't have to keep checking if the method was implemented or not. So for this exercise, go to the API documentation of UI Table View Delegate and have a look and have a think about what protocols you could split this down into. Again, try to think about protocols that end in able if you're struggling. And also, there's no right answer here. You could split this protocol any way you want. There's some obvious ways and some less obvious ways. Part 5 is about dependency inversion. Dependency inversion is probably, in my opinion, the part of Solid which has the most clear-cut impact on improving your code. It's typically defined that code should depend on abstractions and not implementations, which, if you've looked at the past few videos, should make some sense, because there we touched on using protocols, which make abstractions, and making sure code is small and tightly focused. Making sure code doesn't require implementation details of other code is simply one part of that. Now, you might have heard of dependency injection, and that is not something we're going to cover in this video, but we'll talk about a bit later. Essentially, dependency injection can be considered an implementation of dependency inversion, but the actual tenet itself is dependency inversion. So how does dependency inversion apply to real code? Well, depending on abstractions means that we need to ensure our code is structured well enough to support multiple implementations of the abstraction. It also means that a class should not handle fetching its collaborators, but should be past them, and this is where dependency injection plays in. Dependency inversion has major implications for testing, and generally makes testing your code a lot easier. What this boils down to is that a class should not create or find things it needs, and it should not use real classes, but should use interfaces. It's worth pointing out here again that these are guidelines and represent a perfect ideal, and your code's not going to get to that point, but you should be trying to get towards it. Let's try this out in some code. We're going to make a class which loads a list of cute pets from an API, and we're going to use dependency inversion to inject in the network. We create our cute pets loader class, and it's going to need some way of accessing the network. So we could use URL session directly here, or Alamo Fire, but the point of dependency inversion is that we don't want to depend on specific implementations of network loading, but rather a general abstraction. Let's create a property we'll call network, which we can make private, and we pass it in via the initializer. That's the other part of the dependency inversion, where we pass in our collaborators instead of creating them ourselves. We will create the network protocol, which will act as our abstraction. And it's going to have a function which will load some data and return us a result, whether that be a success, i.e. a list of our animals, or an error. We'll make a class now, which will essentially link up together URL sessions API and our network abstraction around it. We'll call it URL session network, and it will implement the network protocol. We'll fill in the stubs and implement it as it should be. Now what's cool here is our cute pets loader doesn't require any implementation detail about URL session anymore. And also it gets a much simpler API. URL sessions API has a few quirks in it, and now our code doesn't need to worry about that.